let's kick things off with a question that, honestly, we probably don't stop to think about nearly enough. We all learn to count 1, 2, 3, but why? Beyond just counting stuff, what are numbers really for? It's a fantastic question that gets right to the soul of what math is all about. And the answer? It's actually really simple, but also kind of profound. Numbers are the language of relationships. See, they don't just tell you how many, they describe how things are connected, how they change together, and how they influence each other. If you can get your head around that one idea, you've got the key to unlocking everything else we're going to talk about. Okay, so if we're going to speak this language, we need to learn the alphabet first. We're going to start with the most basic building blocks you can imagine and just watch as our entire mathematical universe expands and gets richer and richer with every new type of number we discover. So, where do we even start? Well, with the most basic, most intuitive numbers out there, the natural numbers. It's exactly what it sounds like. If you can count it, it's a natural number. 1 cookie, 2 planets, 3 ideas. This is where it all begins. This is the bedrock. And once we have these guys, we can start to picture them, right? We can lay them out on a line, each one a perfect little step, marching on and on forever towards infinity. This super simple idea, the number line, is going to be our map for this whole journey. And for a huge chunk of history, that was pretty much it. But then somebody had a brilliant, revolutionary idea, the concept of nothing, the number 0. It seems simple to us now, but figuring out how to represent the absence of something was a total game changer. You add that one number, 0, to the naturals, and suddenly you have a whole new category, the whole numbers. Okay, so let's go back to our number line. With this invention of 0, we now have a definite starting point, a true origin for everything. It's like we've dropped an anchor. The line still shoots off to infinity in one direction, but now it's grounded by this powerful new idea of nothing. But life isn't always about positive things, is it? I mean, we have debt, it gets cold, you can go backwards. To talk about that, we need to go in the other direction on our number line. So, we take all our whole numbers and give them a negative twin, and that gives us the integers. And bam! Just like that, our number line finally looks complete. It's not just a ray shooting out from 0 anymore. Now it's a true line, stretching out to infinity in both directions, perfectly balanced and symmetrical. This gives us a way, way more complete picture of the world. Okay, but wait, what about all that empty space between the numbers, like between 1 and 2? Well, this is where our universe of numbers splits into 2 really interesting camps. On one hand, you've got the rational numbers. Think of them as the neat and tidy ones. Any number you can write as a simple fraction, that's a rational. Their decimals are predictable. They either stop or they repeat in a nice pattern. And then you have the irrational numbers, and these are the wild ones, the rebels of the number world. You can't write them as a simple fraction, and their decimals just go on forever and ever and ever with no pattern at all. And yeah, you've definitely met some of these famous irrationals before. Numbers like pi, or the square root of 2, or this really important number e. They're not just weird mathematical quirks. They're absolutely essential. They're the filler that plugs every single tiny gap on the number line, making it perfectly smooth and continuous. Okay, deep breath. Our universe of numbers is getting pretty full, right? We've got naturals, integers, rationals, irrationals. It's a lot to keep track of. So to bring a little order to all this beautiful chaos, mathematicians use a really simple but powerful organizational tool. And that's where this incredibly useful idea comes in, the set. Forget the textbook definition for a second. A set is basically just a container, a bag you can put stuff in. The things you put inside are called elements, and you show it's a set by wrapping it all in these curly brackets. It's really just a way to group things so you can talk about them as one unit. Simple as that. Let's make this super concrete so you can see what I mean. Check this out. We've got 2 sets here. We'll just call them set A and set B. Set A has the numbers 1, 2, 3, and 4 inside. And set B has 3, 4, 5, and 6. Got it? Cool. Now we can start to play with them. Now we can ask some interesting questions. Let's start with that first symbol, the one that looks like an upside-down U. That's called the intersection. And it's just asking, what do these 2 sets have in common? What elements are in both A and B? Well, if you look, the only numbers they share are 3 and 4. So the intersection is the set 3, 4. Easy enough. Now what about the other one, the regular U? That's the union. This asks a different question. If we dump everything from both sets into one big container, what do we get? We just combine them all, but we don't list the duplicates. So the union is 1, 2, 3, 4, 5, 6. See? It's just a clean, precise way to talk about what groups share and what they look like combined.
All right, so we've got our numbers. We've got a way to group them up. Now for the really cool part. Now we get to make them interact. We can finally get back to that idea of relationships we talked about at the very beginning. And the tool we use for this is one of the most powerful, most important ideas in all of math, the function.
So what the heck is a function? Honestly, the best way to think about it is like a machine, a really reliable machine. It has one slot for an input and one slot for an output. You put something in, the machine follows a specific rule, and it spits exactly one thing out. The key here is that it's predictable. You put the same thing in, you get the exact same thing out, every single time. Let's walk through one so you can see exactly what I mean. Here's our machine's rule. F of x equals 2x plus 1. That f of x part just means our function's name is f, and it's waiting for an input called x. The rule is take whatever number you get, multiply it by 2, and then add 1. So let's give it an input. Let's say our input is 3. We pop that 3 into our machine wherever there was an x. So now it's 2 times 3 plus 1, which is 6 plus 1, and what comes out the other side? The output, 7. And the beauty of a function is that if you put 3 into this machine, you will always get 7, no surprises. Now, this is all great with numbers, but the real magic, the real insight, comes when we can actually see the relationship. We can take these abstract rules and turn them into pictures, into graphs that show us exactly what's going on. And I really want you to hang on to this idea. Every single function is telling a story. It's telling the story of a relationship between an input and an output. And the graph, that's the picture book that goes with the story. The shape of that line or curve tells you everything you need to know, all in one glance. It lets you see the relationship. Now, up until now, all the functions we've seen have been really obvious, right? The rule is just sitting there, laid out for us, y equals this, f of x equals that. But in the real world, things are usually a bit messier. Sometimes the rule is hiding. And that brings us to our last big idea. What do you do when the relationship between your input, x, and your output, y, isn't spelled out for you? What if it's all tangled up together inside of one big equation? How do you find the function that's hiding in there? Well, that, my friends, is what we call an implicit function. The relationship isn't explicitly stated, it's implied by the equation. Think of it like a puzzle. The rule connecting x and y is in there, but you have to do a little mathematical detective work, a bit of algebra to untangle it and see the function that was hiding in plain sight all along. So look how far we've come. We started just by counting on our fingers, and from there, we've built up this incredible, powerful language of numbers, sets, and functions. This is the exact language that people use to describe everything from the orbits of planets to the chaos of the stock market. It's the language of relationships. So the only question left for you is, what relationship will you describe? Thanks for watching.